Okay, in this video we are going to talk about integrals, antiderivatives, and how you choose a technique for what to use. So let's see what I kind of like go in thinking. So this is the approach that I'm going to use when I'm faced with an integral. This is specific to like Calc 1, Calc 2, Calc AB, Calc BC. I'll let you know when it switches from AB material to BC material, but all of this is stuff you would need in Calc 1 and Calc 2. So the techniques that I definitely know for this level, I would say reversing the power rule is probably the single most common technique that you use all the time. So I'm always going into it thinking I'm probably just going to reverse the power rule on this. Other than that, u-substitution is actually maybe the most common thing you do, right? I think I'm going to reverse the power rule, but to do that, I'll probably do u-substitution first. So usually it's u-substitution and then just reverse the power rule. There's a lot of things that I just recognize. So I look at an integral and I think, oh, that's just the derivative of something I already know. So what would those things be? Like trig functions, the derivatives of the inverse trig functions, the derivative of natural log, and the derivatives of exponentials. Those are things you really need to recognize to be able to find antiderivatives. And then there's a lot of things where you have to do algebra first. So this is typically with things that look like rational functions, so a polynomial over a polynomial. The techniques that you might need to use would be completing the square, long division, and then if you're in Calc BC, so this is not an AB topic, but if you're in BC, you might also need partial fractions. And then the next thing is strictly BC, definitely like a Calc 2 topic, would be integration by parts. Integration by parts is usually pretty easy to recognize because it just doesn't look like anything else. So I will say that the best strategy overall is to have already done a problem like the one you're looking at. And how do you do that? You just do a ton of practice problems. So now I'm going to go through and kind of like show each of these techniques. And I'll do some of the problems full on, and then others I'll just like show the work. So it's about 20 problems, and let's get started. So all of these to me look identical. They all look like I'm just going to reverse the power rule. But for the second two problems, I'm going to have to do u-substitution first. So for the first one, I look at it, I'm like plus 1 times the reciprocal. There you go, 1/4 x to the 4th plus c. The next one I look at, and I'm like, that's basically the same problem, but I really need to do a substitution first. So I would say u is 2x minus 5, which means 1/2 du is equal to dx. I can rewrite the entire integral to be 1/2, and then look at that. That's our original integral. So I'm going to do plus 1 times the reciprocal, which is 1/4 u to the 4th. 1/2 times 1/4 is 1/8. So I'll ultimately end up with 1/8 the quantity 2x minus 5 to the 4th plus c. So again, it's just reversing the power rule, plus 1 times the reciprocal. By far the most common thing you end up doing. So the next one looks the same to me. It looks more complicated, but not so much more complicated because I've seen it before, and I know that when I do my substitution, that cosine that's hanging out there is going to be a part of du. So u is sine of x, du is cosine of x dx, and then I can completely rewrite my integral as just the integral of u cubed du. There it is again, plus 1 times the reciprocal gives me 1/4, whatever u was, so sine to the 4th, and then plus c. So that's how reversing the power rule comes up, and you're going to mix and match it with u-substitution. Don't be afraid of that. Do a lot of practice problems, and you'll definitely be on top of it. All right, the next thing, just stuff that you have to recognize or you should recognize. So for the first one here, so all of these, take a second, look at them. Now I'm going to go through and do them. The first one I look at, cosine is the derivative of sine. I recognize that. But I need so I'm going to do these the way that I would do them. You might just do u-substitution. I need a 3 on the inside, so a 1/3 to balance it on the outside. Now it's perfect. It's 1/3 and sine of 3x. But all of that was kind of kicked off by the fact that I know that cosine is the derivative of sine. For the next one, I see secant tan. I know secant tan is the derivative of secant. So I'm thinking this is just going to be secant of 5x, but I need to do a substitution. So I'm thinking u is 5x probably. So I need a 5 on the inside, a 1/5 on the outside. This will be 1/5 secant of 5x. So experience tells me how to do a lot of these. And if you do use substitution enough, you'll eventually be balancing out the way that I am with the 5 and the 1/5. If not, just do the substitution. Let u equal 5x, 1/5 du is dx, make all the substitutions, and you should get the same answer. All right, for the next one, if I see a radical in the denominator, I'm kind of thinking maybe I should make u equal the thing inside the radical. That's not going to work in this case, and I probably would go down that road, see that that doesn't lead to the answer, and then switch up my technique. So now I see a radical in the denominator, and this kind of just looks like the derivative of arcsine to me. That's probably the last thought that I have with these types of things, but definitely this is the derivative of arcsine if I make a substitution. So if I let u equal 2x, which means 1/2 du is equal to dx, I can completely rewrite the integral as 1/2 the integral of 1 over radical 1 minus u squared du. That's perfectly the derivative of arcsine of u, so I will get 1/2 sine inverse of 2x, which is u, plus c. So it's really the recognition, but keep in mind, there's a lot, like people who know what they're doing go down a lot of false paths, right? They like start the path, they're like, I'm gonna make u equal 1 minus 4x squared, but if that's the case, then du is negative 8x dx. I don't have an x in the numerator, so that can't be right. So now I have to think like, what else do I know with a radical in the denominator? Oh, it's arcsine. Got to do a lot of problems to recognize it, but once you recognize it, the problem usually isn't that bad. All right, the next one I look at and I think, I don't know, just let u equal the denominator. And if I do that, u is 1 plus cosine, du is negative sine of x dx. I can rewrite this whole thing. It's going to be negative 1 over u du. And now you have to, so if you try to reverse the power rule on that, make it u to the negative first, when you add 1, you get u to the 0 times the reciprocal, which is 1 over 0. That's problematic in a lot of ways. This is where you have to recognize natural log. So when you try to reverse the power rule and you end up with a problematic situation, like to the 0 power times 1 over 0, it's definitely natural log. So knowing that, I know that this will be negative natural log absolute value of u, or negative natural log absolute value of 1 plus cosine of x plus c. I'm putting in the absolute value. I always put it in. You kind of don't technically need it there because 1 plus cosine is always greater than or equal to 0. But I think that putting it in is advantageous because you need it when you need it. And if you don't need it, then it's just there. It's not hurting anyone. So absolute values for sure. All right, I look at the next one and I think, I've seen this a million times. This is just the derivative of an exponential. So it's like e to the u. U is 3x to the fourth. So then the derivative of that would be 12x cubed. There should be a 12 on the inside, and then balance it with 1/12. And so now this is perfectly the derivative of e to the 3x to the fourth. That just sounded weird when I said it in my head. So this is going to give me 1/12, and then e to the 3x to the fourth plus c. Now, if you haven't done a billion problems or you don't like that, I recommend every time you hit an exponential that you have to integrate, let u equal the entire exponential. If you do that, it's going to work out that you end up integrating du basically all the time. That's going to happen in the next example, I think. But that's how I would handle that if I wanted to show a lot of work, which I don't want to do. But if you wanted to, I would let u equal e to the 3x to the fourth and go from there. All right, the next one, it's an exponential. To integrate an exponential, I think to myself, I'm going to let u equal the exponential. So I'm just going to let u equal 5 to the x plus 1. Now the key here is I need to now remember how to find the derivative of 5 to the x plus 1. So that's a thing we need to know going into this, or we're not going to be successful with the problem. But I do know that the derivative of, let's say, 5 to the x is 5 to the x natural log of 5. So I was able to use that to figure out what du is. You have to know that. So recognize the derivative of a to the x, the derivative of e to the x, the derivative of arctan, the derivative of arcsine, all the derivatives of the trig functions. You have to bring those with you, otherwise you're not going to be successful. All right, so then this will become, just rewrite the whole thing, 1 over the natural log of 5 integral of du, which takes us to 1 over natural log of 5 times u plus c, and then finally 1 over the natural log of 5 to the x plus 1 plus c. So recognizing a thing is like really the easiest way to do it. It's like, how did I figure that out? I already knew the answer and I just had to take care of the minor details. And there's no substitute for practice to get good at that, but make sure you memorize. All right, let's take a look at the next thing. So this is where we're going to start doing the algebraic type of things. So most of these will look like rational functions. If you see a rational function, you start thinking kind of the way that this is going. But for these, to summarize again, I basically was doing u-substitution, recognizing the thing, and then just a lot of experience. Here goes. So we have x plus 5 over x minus 3, and we want to integrate that. Well, I look at that, and I'm like, these are the same degree. Anytime I see that, I know I need to divide. So if you have the same degree, you need to divide before you can integrate. I'm not going to show the division. I'm just going to show what it works out to. So we get x plus 5 over x minus 3 is the same as 1 plus 8 over x minus 3. All right, so integrating the left-hand side is the same as integrating the right-hand side. So to do this, what I really do is integrate this thing. Now, keep in mind, I don't know why. I think it's because the division is like a lot of work. Students all the time, well, people, let's say, it's not necessarily students, like anyone, they often forget that they also have to integrate the 1. They get so excited and they just integrate 8 over x minus 3. Don't forget, you're integrating the entire thing. Integral of the left side equals the integral of the right side. And then if we do this integral, we're going to get x, when we integrate 1, we're going to get 8 natural log absolute value of x minus 3, and then plus c. So if you have the same degree, divide first, then integrate. Well, what about the next question? It turns out that actually, if the degree of the numerator is greater than or equal to the degree of the denominator, you should divide. So I'm going to do the division. I'm not going to show it. I have videos of doing long division if you need to see those, and synthetic division if you want to see those. Just look them up on the channel. You'll find them. So when I divide this, I get x squared plus 2x minus 4 plus 3 over x plus 5. And I'm going to integrate that. So integrating this, it's 3 times kind of reversing the power rule, and then 1 that I recognize to be natural log. So I get 1/3 x cubed plus x squared minus 4x plus 3 natural log of the absolute value of x plus 5 plus c. Please don't forget the absolute value. Those are the saddest points to lose on something like this. You do all this work, you get to the very last step, and then you're like, I'm going to give up half a point, or I'm going to give up a point. Don't do that. Put in the absolute values. All right. Strictly speaking, if you're a clever person or a person really devoted to a technique, you actually could have done those 2 problems by letting u equal the denominator and then just converting everything. The second problem would be particularly brutal if you did that, but you could do it. Sometimes that doesn't work. So I'm going to run through one more problem that's an example of this. So the integral of x squared plus 3x plus 2 over x squared plus 1. All right, so in this case, I would do the division because the degree of the numerator and denominator are the same. So I'm going to do the division, get the integral of the quantity 1 plus 3x plus 1 over x squared plus 1. This is still something that I need to work on, right? So like that second part there is a little complicated. What I would do, I would initially try to let u equal the denominator and just see that like u-substitution doesn't straight up work on it, but I can break this into 2 fractions. So I'm going to take this and break it up. So now I have the integral of 1 plus 3x over x squared plus 1, which looks a lot like a natural log to me. And then I also rewrote it as 1 over 1 plus x squared, because I think in terms of if I'm thinking of arctan, I'm thinking 1 over 1 plus x squared. I'm not thinking 1 over x squared plus 1. Rewrite it so it looks the way you want it to look. Well, the way I want it to look, really, so that you can just recognize it. And now these are just straight up integrals, right? So the integral of 1 is x. For the second integral, I would need a 2 in the numerator, so a 1/2. So that's where 3/2 is coming from. And then natural log absolute value of x squared plus 1. You don't really need absolute value there because x squared plus 1 is always positive, but just put it in and don't worry about it. And then the integral of 1 over 1 plus x squared is going to give us arctan. All right, so those are rational functions where the degree of the numerator is greater than or equal to the degree of the denominator. Let's take a look at another type. So, and yeah, with rational functions, there's like a lot of thought processes you need to go through, but the more you practice, the more you'll recognize them. And the division one, I think, is the easiest one to recognize because it's like, what else are you gonna do? Like you can't just do a substitution and get it. You're gonna have to divide and then integrate. All right, so here, the degree of the numerator is less than the degree of the denominator, so that's going to be, I'm not going to do division, I guess, is what I'm trying to say. But I do notice if I just make u equal the denominator, that's going to fail. It's not going to work. Also, the denominators in both cases here do not factor. If both of those things are true, I'm probably going to have to complete the square, especially if there's a quadratic in the denominator. So I'm going to complete the square on these. When you do this, you frequently end up with arctan, sometimes natural logs. Let's see. So again, I'm not really going to show the work, but I will point out that for the AP exam, it is often the case that you can just kind of rewrite the denominator. I mean, this is completing the square, but what I'm doing basically is I'm going to take the 10 and just to break it up into 9 and 1, because x squared plus 6x plus 9 is a perfect square. So I'm just breaking that up. But you can do normal completing the square. And again, I have videos on completing the square. I just don't want to go through all of the algebra in this video because it's already going to be a long video. So once I have this, I can rewrite this as, because it's arctan, I'm going to write it as 1 plus the quantity x plus 3 squared dx. And then that is definitely the arctan of x plus 3 plus c. So why did I think to do this? U-substitution didn't work initially. The denominator did not factor, and there was a quadratic. So I'm like, I'm just going to complete the square and see if it works. Now the next one is the same, but like a little different because we're up at a higher power. We're at x to the 4th, but I see x to the 4th and x squared. That could also be a perfect square, just like a different perfect square. So I'm going to complete the square in the denominator and see what happens. So again, I break 50 into 49 and 1 because like u squared plus 14u plus 49 would be a perfect square trinomial. So I'm breaking it up. But again, if you need to review it, go find a video for completing the square. That's all I did here is complete the square. I'm going to rewrite this again, and I'm going to do it in basically the exact same way. So it's the integral of x over, I bring the 1 to the front because if it's arctan, I want it to be 1 over 1 plus u squared. And then I have u squared, so x squared plus 7 quantity squared. If I'm doing the work, so like I think that I just need a 2 in the numerator and a 1/2 on the outside, but if you don't think that, you can do a substitution here, right? And this would be your substitution, but I think 2 in the numerator, 1/2 on the outside, this is going to be 1/2 arctan of the thing that I'm squaring, so x squared plus 7 plus c. So I have videos on integrals that end up with arctan, which I definitely recommend. I'm doing a lot of completing the square in there and some like factoring type things. Check that out if you need more practice with this. So completing the square does come up in another scenario. So these were both rational functions, which is the most common. It could also come up in an integral that looks like this. The integral of 1 over radical 24 minus 10x minus x squared dx. So like this would be, you try to make u equal the thing in the radical, that's not going to work for you. In my mind, I kind of think like if you have a weird radical in the denominator and u substitution fails, you have to be thinking that this is arc sine. So I'm going to complete the square and just write it down. So I get the integral of 1 over radical 49 minus the quantity x plus 5 squared. Then what I'm going to do, because this is a 49 and it should be a 1, I'm going to factor 49 out of the radical, out of everything in the radical. So if I take 49 out of a radical, it becomes 7, but it's in the denominator, so that's really 1/7. And then the integral of 1 over 1, and because I took 49 out of x plus 5 squared, that's really dividing by 49. So I can rewrite it as the quantity x plus 5 over 7 all squared, which would be x plus 5 squared over 49. So I just rewrote it as like u squared. So u is x plus 5 over 7. So I really need a 1/7 in the numerator and balance that with a 7 outside. And now this is really nice because the 7 and the 1/7 outside cancel, and we just end up with the arc sine of x plus 5 over 7 plus c. But what's the point of this? The point of this is when you see quadratics somewhere, try completing the square. If you've already run through other options, that shouldn't really be your first thought. Your first thought should be like, does u substitution work? Should I be dividing? You know, like, do I recognize it? But when all else fails in this regard, if there's a quadratic, complete the square. Probably arctan, probably arcsine will show up. All right, so If you're in Calc AB, you're done with the video. Good luck. Go do a lot of practice problems. If you're in Calc BC or Calc 2, keep going. So the next thing that might happen is you could have a rational function, and it might be that the degree of the numerator is equal to or greater, in which case you'll have to divide. It might be that it's already a proper fraction and you've tried u-substitution and it failed. So if you have basically the same issues with u-substitution or numerator denominator, you have to start thinking maybe this is partial fractions. And the key here is that the denominator will factor. If the denominator doesn't factor, it's probably a complete the square situation or just u-substitution. If the denominator does factor, then it's probably partial fractions. So in this case, I'm going to do partial fractions. I'm just going to do it. I have a lot of videos on this. Check those out. But the partial fraction decomposition is what you should search for. Would give me the integral of 5 over 7 quantity x plus 4 plus 2 over 7 quantity x minus 3. When you do partial fractions, you get natural logs all the time, arctans often. Just depends on what the factors end up. So this, when we integrate, 5/7 natural log absolute value of x plus 4 plus 2/7 natural log absolute value of x minus 3 plus c. So it's really a checklist. You're like running down. U-substitution, no. Completing the square, no. Now I'm trying partial fractions. Honestly, if you do enough of them, this problem, looking at it, looks exactly like I would try u-substitution, it didn't work, and I would immediately do partial fractions. It wouldn't occur to me to try to complete the square or anything on this one because it definitely looks like a partial fractions problem. The next one I look at and I think, I don't know. I'm going to do long division first because the degree of the numerator is 3 and the denominator is 2. So I should do division. So long division first. That gives us this. Quantity x minus 3 minus x plus 2 over x squared plus 7x plus 12. I look at that denominator and I think that definitely factors. And since that factors, I'm going to try partial fractions. I mean, I really should have tried normal u-substitution and see that it's not just natural log. But the denominator does factor, so partial fractions it is. I've done the partial fractions. I'm just going to write it out again. Be really careful on this one, though, because you get x minus 3 minus, I did my partial fractions on x plus 2 over x plus 4 times x plus 3, not negative x minus 2. So I did minus the whole quantity and then the result of partial fractions. So 2 over x plus 4 minus 1 over x plus 3. Use parentheses when you need them. They will help you out. That's like what their purpose is in life. And then we just integrate. So I'm going to get 1/2 x squared minus 3x. Now don't forget to distribute this negative. So minus 2 natural log of the absolute value of x plus 4. And then minus negative becomes plus. So I wrote it in red just to like emphasize it. Natural log of the absolute value of x plus 3. And then plus c. All right, so that's partial fractions which could come up. And then the last thing that can come up really when you're in like Calc BC, Calc 2, because you start to like run out of techniques. And really, are there that many other techniques? There are a couple other substitutions, but like by the end of Calc 2, you know the bulk of the techniques of integration. And then it gets into really special cases. The last thing that you really need going into these sorts of things is integrals that look like this. These are going to be integration by parts. So if you have like a polynomial and a trig function, a polynomial and an exponential and a trig function, or just something really wacky, you start thinking, this is probably integration by parts. So I'm not going to like go through each of the steps on this, but if I have x and sine of x, I'm definitely going to choose the thing that goes to 0 when I take derivatives to be u. So like if I take the derivative of sine over and over, I never really get 0, right? It's periodic. It'd be cosine, negative cosine, and so on. Whereas if I take the derivative of x, I get x, 1, 0. Definitely choose the one that goes to 0 if you have a choice. So my work for this would be u is equal to x, which means du is dx. dv is sine of x dx, which means v is negative cosine. Then I do uv minus the integral of v du. And we go from there and get that. Did I get that wrong? uv, v du, minus negative is plus cosine. And then, yeah, there should be a plus sign here. Hold your horses. This right here, that's a plus. Okay, there we go. There we go. I got the work wrong, but I got the answer right. I don't even know, which means the one I did initially, I like did the work wrong and got the wrong answer, but it worked out to the right. That's like the best feeling is when you do the wrong work, but you get the right answer. Like, it's not good, but it feels good. Anyway, that's our answer, right? So for the next one, I'm going to do the same thing, except it takes more than one step. So I'm going to use the table method. I'm just going to throw the table method out there. I have videos on that. Also, I do it slightly differently from how some people do the table method. For my V column, I start with dv above it, and then I integrate, and that first entry there is the integral of dv. So it's actually v. Everything in that column is actually v, not dv type things. So the integral of e to the x is e to the x. All right, so what do we do with this? Well, we just multiply these, so that's x squared e to the x. And then the sign is the sign in between terms of the answer. So this minus is minus. Multiply these, 2x e to the x. The sign between this term and the next term will be plus. So plus, multiply these, 2e to the x. And then the next row would start with 0 because the derivative of 2 is 0. So we don't write anything. We're just done, plus c. All right, so those are pretty standard integration by parts problems that you'll see. In Calc 2 or like a BC test, not the AP exam, but like in the class, I would think you might see integration by parts that loops on itself. I'm not going to cover that here because this is more like a preparing for the AP exam type video. But I do have videos where an integral will loop on itself. So the original integral comes up again as you're doing integration by parts. Those are pretty neat. But the next one could come up. So like the integral of arctan of x dx. You look at that and you just have no idea what to do. Like, what am I even doing? I don't know the integral of arctan, and that's the question. So like, what do I do? It's probably integration by parts where you're going to make the weird choice of dv is dx. So instead of like something, like a function, dv is just dx. It's always amazing to me that this works out, but it does. Here's what the work will look like. U is arctan, so du is 1 over x squared plus, dx. And then dv is just dx, which means that v is x. So I do u times v, so that's x arctan of x, minus the integral of v du, which is x over 1 plus x squared dx. You can actually integrate that. And so we end up with x arctan of x minus 1/2 natural log, absolute value, kind of optional here, but put them anyway, 1 plus x squared plus c. And those are the techniques that I use. That's how I decide what to do. So I basically go from the least complex to the most complex. And then I think of integration by parts as kind of on its own with like, nothing else is working, and this is a weird collection of functions. It's probably integration by parts. So I'm going to end this video here. I hope you found this helpful, and good luck.